Hi, I'm Toby K. How's it going? Welcome to day 11 of Advent of Code 2024. This is a solution in v4 Gamma, which is a visual programming language based on .NET. You've probably noticed it's not the 11th of December 2024 anymore. It's now the 19th of February 2025, but that's family life for you. I knew this particular one was going to be tough. I'd already seen there was some discussion in the Advent of Code thread on v4.org. So I had a crack at it, got through the first part okay, but for the second part, I definitely hit a wall. I was at the end of my knowledge, which is a bit ego bruising, but ultimately good when you're doing these kind of challenges. Time for me to learn new techniques, and then this is something I can also hopefully show you. To come up with my final solution for the second part, I looked closely at the solutions from Greg and Yar in the forums. So big thanks to them for sharing their knowledge, and also checked out some solutions in other languages on Reddit and so forth. So I'll go through everything. I'll also go through their solutions, show you all the different ways you can do something like this. But first, let's start with what we're actually meant to achieve here to solve this puzzle. Okay, so what we're meant to do for this one, we're on the planet of Pluto. We're looking at a bunch of stones. Every time we blink, the stones change, and they follow some rules based on numbers that are written on the stones. Sometimes the numbers change, and sometimes some of the stones split in two. And what we're basically meant to find is the total number of stones based on the number of blinks. And the first part of the challenge asks you, what happens if you blink 25 times? And you start with some stones like this, blink 25 times. How many stones do you finish with? Second part of the challenge was just increasing that to 75 times, which is so many that you need to take a different computation approach. I'm going to visualize, because that's what I ended up making, a visualization of what this looks like to solve this. Let me just do a slightly simpler one. So if you started with the number 2020, you follow one of three rules when you process it. The first rule is that if it's a 0, it turns into a 1. And we see that here, there's a 0 that turns into a 1 on the next blink. The second rule, and you follow these rules in order. The second rule, if it's not a 0, then the next rule you look at is, does it have an even number of digits? In this case, it has 4 digits, in which case you split it into two numbers. So 2020 splits into 20 and 20. The last one you look at is if neither of those first two rules apply, which is what's happening here, you take the number and multiply it by 2024. So 2 times 2024 is 4048. Now, those numbers matter as the tree grows, but then ultimately what we're counting to get the final result is just how many end nodes we end up with after, in this case, 4 blinks. So we're starting here, and we think about blinks remaining. So starting here, we haven't done any blinks, and then here we've taken 1 blink, we've taken 2 blinks, we've taken 3 blinks, and at the bottom we've taken 4 blinks, and we stop. That's basically what we're meant to try and find, and you can see these purple numbers. I'll explain this more. These are the counts. It's 1 at the bottom, and then these nodes are also counting up how many of those final children they have. So this number 6 here is the result, and that's what we get there. Here's my solution for part A. This is just a simple brute force solution. Let's go through it. So here's the puzzle input, which is just a string of numbers separated by spaces. So we just use a split by space. We then pass those as a spread of integer 64 unsigned. And that was simply based on my instinct that these were going to be pretty large numbers. Once you've multiplied by 2024, not 25 times, but a bunch of times, you could end up with a very big number. And also based on the usual advent of codes, it seemed likely that it was going to get pretty big. Quite sure it wasn't going to go negative though, from the way the rules work. So happy to use the unsigned version of that, which has a higher ceiling than the signed version. Okay, then what we do is we have this process that applies the rules. Then there's those 3 rules, rule 1, rule 2, and rule 3. Rule 1 is if the input is 0, it makes the output 1, and it has this compose next spread where it's building up based on this input. But if it's not that, then try the next rule. Then if we try the next rule, what we want to do is this operation that splits the number if it's an even number of digits. So first we need to work out how many digits are in the number. And to do that, we actually do this thing where we have the powers of 10, which we just generate once. So here they are. Here's a whole bunch of them. And to do this integer 64 unsigned, this is how many we need, 18. And then we simply run a greater than operation a whole bunch of times. Number of digits. Here it is. Yeah. We take our input number and then powers of 10, and we say, okay, when do you exceed one of those powers of 10? The moment you exceed it tells us how many digits are in the number. Simple as that. And then we split the number into its front and back halves. We take the digit count that it's in. We take again the powers of 10. So we want to get that number. And then you divide it. So yeah, in this case, if it's 1,000, divide it by 100 and you'll get 10. And also take the mod of it by 100 and you'll get the other half. In this case, it's 1,000 and the last two digits are zeros. So it's a 0. Yeah, you can see that example happening here. So that's how that works. It's a numeric way to split the number into its front and back halves of digits. Okay, rule 3. This is simply multiplying it by 2024. The only other interesting thing here is it's possible, because it has to give 2 items, that we always actually have a spread output. Even though the rule 1 and rule 3 only produce 1 item, rule 2 produces 2 items. So then we have a variable number of items that will come out here, 1 or 2. Those have to be flattened and then turned into through the accumulator. That's then fed into be the next inputs for the next blink, the next step. Then back out here, we output the result. The count of the result is the number of stones. In terms of time, 25 blinks is totally feasible to brute force. Even on this 4-year-old, not particularly amazing laptop, I'm getting, a few frames a second. But once I turn that up to 30 blinks, 35, I think, I couldn't push it past 37 or 38 before I was filling up my memory and basically, getting something that was never going to return. You could, of course, I'm sure there's some hardware out there, but what they're pushing us towards in advent of code is to find a solution that's a little bit faster than this. So let's talk about how to do that. So the technique we're going to use to speed this up is called memoization. A big thanks to Greg on the forums who put forward a solution that uses this. So the way it works, here's the tree we had before. If I turn on memoization and run and visualize it again, so this time you notice the first one gets split into 2, 20s and 20s. If you imagine it's working left to right, basically when it comes to doing this 20 on the right again, it says, I've already done a 20 at 3 blinks and it ended up having a count of 3. So I can simply recall that and use that result here to get the total answer of 6 again. And that's how we speed this up, and it saves doing all those operations that would be below that 20 again. There is one more new structure we need to understand before we have a close look at the solutions, and that's BigInteger. So it was my instinct before that we would need a pretty big number, but it turns out a 64-bit integer isn't big enough. Once you're doing 75 of these blinks, then you can be even bigger than that. .NET has a solution for this called BigInteger, which is an integer that's not limited to a specific number of bytes. It can expand and take as many bytes as it needs to represent a very big number. If you want to use this in v4, it's not in the core library. Actually, if I go back for a second, so you see it was called system.numerics.biginteger. What we have to do is go new VL document. If I put BigInteger now, there's nothing, and I can tell you it's not in an existing VL library. What we have to do is go Files, add .NET Framework Assembly, and then go down until we get system.numerics, double click that, press OK, and now it's here. And you find BigInteger, and the way we use it is you always want to create big integers, and you can create them from other numeric types. So here's 1, here's a 0, and then there's a 5 or whatever. Obviously, if you have a very large operation that would create a big integer, you've got to convert them to big integers first. So as in, it's already got to be the big integer type. If you want to multiply an integer 64 at max value by another integer 64 at max value, convert them to big integers first, so that then once it's on that side, it can support doing that. And just to share with the math operations, you're like, okay, I want to multiply them, but it says unable to resolve the adaptive node. That's because a big integer isn't in the adaptive types, but if I double click on it, I can find it there. So that'll work. And then 0 times 5 is 0, 5 times 5 is that, and let's do it. Integer 32 max value times integer 32 max value is apparently a very big integer. So that's how that works, and that's what we need to track the stone numbers, which can get very big. Okay, so now let's look at the solution from Greg, which is a very nice recursive solution to doing this. So I've slightly modified this with a little extra log that actually shows the steps, which is what I needed to do to even understand it. So the way it works is it takes, similar to as we saw before, list of numbers, or you can just take one number. You say the number of steps. It converts those numbers to a big integer. The dict request is just my monitoring system here, so we won't worry about that. And it also has this mutable dictionary, and the mutable dictionary is the memoization dictionary. So what it does is it operates on each one of the integers in this list, in the top level list, and they get expanded. So in fact, these can essentially all be their separate path of expansion, and then it adds those. The count of adding them is only an integer 64. But the actual operations themselves internally still need to be big integers. So that is, actually, if I go back to my graph, the stone numbers need to be big integers, but the actual count only needs to be an integer 64, just to be clear. Okay, then the application is over here. Do we start with count only cached or count only core? Let me go back. We start with count only cached. So that's this one. So first thing it does when we go in here is it tries to get the value from the dictionary if it's already visited that stone before. If it's not, then it runs count only core, which we'll look at in a second. The key for the dictionary that it's looking up is a value tuple. The first item is the big integer, so the stone number. The second item is the blinks left. And again, if we go back here, this is doing this. It's like, okay, I need to find where's stone number 20 that's been resolved for 3 more blinks of processing. That's what we need to look up. So that's why that's the key to the dictionary. Over here, this is just my log stuff, a dict request to show me what's going on in the dictionary. Before we go into this count only core, note the set item here. So it's taking the result from this and adding it to the dictionary and using that same key, the big integer, the stone value, and the number of steps left. So that way items are being added to the memoization dictionary to be retrieved later. Okay, let's look in count only core, which is down here. So first there's an outer if loop, and that only triggers when the steps left, blinks left, is greater than 0. When it's 0, it always returns 1 because that's the count. If we're at the end node, no blinks left, every node is resolved into a count of 1 at that point. Okay, inside we have these 3 if blocks that are similar to what we've seen before in terms of the 3 conditions, the 3 different rules that can be applied to the stone. If it's 0, so the big integer has to be created here. If it equals 0, then the result is 1, also as a big integer, and then it runs count only cached. Count only cached is the first operation we went at back here. So that's a little confusing, and this is what I mean by this solution being recursive. I'll go into how that works in a second. First, let's look at the 3 steps. The second one is checking whether the stone is a even number of digits, the stone number. And it's doing this through a string-based method. So it's converting it to a string and then counting the string numbers. I suppose the way I did it was mathematical, but string also works great. And this solution runs really fast. So obviously it certainly works well enough to solve this. And then it's again turning those into, if this is true, it is it mods 2 with no remainder left over. That means it is even number. That means it runs the operation where it gets the front and back halves of that number and splits them into 2, again, big integers, runs count only cached on them. And then it adds the results. And you're like, wait, hey, why are we using a plus here? I thought we want the stones to continue down the tree. Continuing down the tree happens in here. That adding the plus is the counts. So the count that's eventually returned here is from each branch of that tree returning the count that's then summed. This one at the bottom is the multiplication times 24. So the input big integer is multiplied by a 2024 big integer. Again, it runs count only cached. So how does this work in terms of the recursive aspect? What the recursion is going to do is enable these 2 operations to traverse the tree in what's called a depth-first manner, a depth-first search, even though ultimately search is not really what we're doing here. So when we look at this tree here, the way this needs to traverse the tree, when I said it went from left to right before, we start at the top and then it processes 20. In fact, I'll use my visualization that I'm going to use later. So we start at step 0. Step 1 is to go this way down the tree, then split that, but then continue and finish the left side. And then you're going through in this order. The next one, right, go back up, and then eventually do that one. The reason you have to do it in this order is because for this lookup to be effective later, you need to have traversed the entire tree down to the bottom on this side. If you did it breadth first and just did every blink its entire width across the tree, then you wouldn't have entries in the dictionary already when you process over here that tell you the result all the way to the bottom of the tree. Okay, how does this code actually achieve the depth first search? Let's step through it, and let's say we're starting with a stone that has a value of 0 written on it, and we're going to do 2 blinks. So we start up here, it says the stone is 0 with a value of 2 blinks. Does that exist in the dictionary? Nothing exists in the memoization dictionary, no. So we're going to here count only core. Then it goes through, there's more than 0 steps left, so that means this code's going to run. It's going to go, does this equal 0? Yes, it does. So this code block runs. So now it's going to create a big integer of 1, which is going to be the next stone value. So basically the stone is transformed to 1, and it's going to decrease the steps left and run this code again up here. So up here it goes, okay, this has a value of 1 here, and on steps left there's 1. Does that exist in the dictionary? No, it doesn't. So now it goes in here again. Again, we have more than 1 step left, so it runs this code. Now it goes through here. Neither this block or this block is satisfied. We use rule 3. We multiply it by 2024. We go into the count only cached. In the count only cached, we put 2024 with 0. The steps were reduced to 0. 2024 with 0 steps left. Does that exist? No. So then we go into count only core. Does that exist in the dictionary? No. So then we go into count only core. This time, steps left is 0. So actually we don't run any of this, and we just return 1. 1 is returned here, and it says, okay, I'll save that in the dictionary if I try and look for, and this one, it's a little pointless to save anything with steps left 0 in the dictionary, because anytime steps left is 0, it could just be 1. Could be a special case that handles that, but for argument's sake, I'll just talk through it. So that says, yeah, for a key of a value of 2024, steps left 0, that has a count of 1. Then we continue kind of going back out of what we did. So now we go back out a layer. This count only cached is resolved. It outputs that output of 1. And then we're going backwards now. I think it was out here. That outputs that the result was 1. That goes all the way at that output. Then we come back out here. Again, now we should be back at steps left 1, with the input value at the time was 1. So when you have 1 and 1, that's saved. That's 1. Goes back out. And then again, we go backwards. At the time we ran this, we come out here. The count is still 1 that's output, comes out there, and then basically, again, that's set in the dictionary. It says, okay, if your input is 0 and you have steps left 2, then your output is 1, then your count is 1, then that's saved in the dictionary. In this case, we've resolved our whole tree. It only really gets interesting when some of this 2 split happens, but basically that's just talking through very simply is how the recursion happens. And that's why I put this little dictionary tracker in here so I could track that happening. This is 2020 with 4 steps, and you can see it going through all here. And actually this is doing exactly what we pictured here. One of its almost last step is to read a value from the dictionary, which is value 20 with steps 3. It finds that in the dictionary finally with a count of 3. I hope that was vaguely clear how the recursion works. It's a little hard to understand, and that's actually probably the biggest challenge with recursion generally. Unless you're doing it a lot, this sort of thing gets quite confusing. It took me quite a while to get my head around this solution. And that's why for my solution, I decided to try and do it without recursion. So my code, and also Greg's a bit of a legend, my code is definitely not as clean as this, but I'm going to take you through it and show you how to do this without recursion. Okay, so let's look at how I did it. First off, there's a bunch of stuff here that's just for logging and visualization, which you don't need strictly to get the solution. I needed it to debug and build the thing. You can turn off the logging, it would run slightly faster. So that's to do with the logging. This node counter is also to do with the logging. The memo dict is the memoization dictionary, and the stack. Stack's pretty important. If you don't know stacks, a stack is a structure, kind of like an array or something. a particular kind of collection. And the way it works is, yeah, you put items in the stack. Thanks, random Google Images, for this, by the way. Put items in the stack, and then it stacks up, and then you can only access what's at the top, I mean, normally, and then you can remove it, or actually, you've got three operations. You can add something to the top with a push. You can peek, which is just looking at the top without removing, and you can pop, which is taking something off the top. With the visualization, I'll show you exactly how this is relevant for navigating, doing a depth first search of a tree. But trust me, we need a stack. And then, yeah, we go in here, basically similar to before, we're going for each. We could have a whole stack of numbers. We want to go for each, process for those, add it all. I actually used BigInteger for the count as well. Could have been integer 64. We learned from Greg's solution, but I also made that a BigInteger. Why not? So final stone count comes out down here. There's this all complete thing. I will come to that later. Total iteration count, which isn't much for this with 220 and 4. If I go in here, you can see there's a bunch of stuff again on the right. That's just for logging. Most of what we're looking at is here. But actually, I think I'll go to the visualization now and we'll step through how this actually works to do this without recursion. So let me turn off my little thing there and we'll go back to the start. Okay, so again, we're processing 2020 with 4 steps. And the first thing we do is expand this node. And what we've done, every time you see these like rectangles added with the outline, we're adding an item to the stack. So the first thing it does is processes this and it expands. It does what's called expansion. Expansion is whenever it looks at a step on the node and runs the rules, looks at the value on the node and runs the rules. In this case, it expanded it to 2 new nodes that are both 20. Then look at the next step. It adds this to the stack to process it. Then it expands it and says, okay, that's 2 and 0. Then it adds this one to the stack. It processes it, then expands that one. That expands into only one. This is 4048. Adds that to the stack. Then we get expands to these, and actually because at the last step, it adds these to the stack, but then immediately they should resolve to their count, which is just 1. Now, so I'll step between these. This was added to the stack, and when it was resolved, it was removed from the stack. It was popped from the stack. Now we go back up. When we go to the next step, we've gone up, and what's actually happened is it's gone to this node and said, do you still have children left that are not yet processed? Yes, it says I've got this child left. So this is then added to the stack, run the processing step for that. It's resolved as this count. Then again, it looks at, and that's popped off the stack again, which leaves this one, 4048, as the one that's on the top of the stack now. And now this lets us go backwards. So now it says, okay, I'll process this. I've gone through some conditions. I know you don't have any children left. So your last step is to add up the counts that belong to your children. And that's what this one does. Then this is the next on the stack. Goes through this. Again, it's resolved all its children. So it's going to collect its count. Back over here, what's going to happen is it's still got a child, so it's going to add that to the stack. So I go through, and you see it's the exact same thing. Now it goes backwards. When we get over here, on the right still has to be resolved, but here is where it finds the value in the dictionary. In this case, that is the same as this one on the left, so they both resolve to a count of 3. And last step is it comes up here. Technically, there's one more step where it actually returns that value. And we end up with, a total count of 6. Okay, whoops, I'm looking at the wrong one. Okay, the way that actually works in here, once I go, in here. So first there's a little if we need to be having more than 0 blinks. Then we want to, here, basically what we're doing is creating putting the first element that came in on our stack. We're clearing the stack, and then, the first element comes in here. And every time we process a node, when I said we're putting on the stack, we actually put a thing on it called a node frame, which is a structure that takes care of a few things. This stuff is mostly for visualization. This is what's actually used. Basically, the value of the stone, which is the BigInteger, remaining blinks. We need to know at this level in the tree, this node, how many blinks are left. That's actually not written as a number there, but I can tell you it's 4 at the top, 3, 2, 1, 0. We need to know if this has children, and there's It's using a list of children. There's another object called childstone. Then there's the accumulated value. So that's that 3, that count. Whether it's expanded or not, which means whether it's run the processing rules. Then the process child index. Basically, the process child index is how many of your children have you processed. So when we're doing that, that's going to be 0 when it hasn't done any, 1 when it's done the first one, 2 when it's done the second one. That's compared to the count of children, so it knows when the thing's complete. Some other operations there we'll come back to. Okay. So that's a node frame, and a node frame is added to the stack, and that first node frame that's added to the stack is, let me go back here, is just 2020. Okay, then there's this repeat. So this repeat loop, this is how we iterate through this without recursion. We just run a repeat loop a lot of times. And in this case, the maximum we can put in here is integer 32. If I needed more than that, I would need to do a repeat loop and a repeat loop, both with max value integer 32. Now that's a lot of repeats, so we definitely want to have, and before I made that a very large value, I used a break, I made sure my break condition was going to work with some debugging. We definitely want a case where we're actually breaking that early, using the break pin here, and it breaks when nothing's left on the stack, because things are popping themselves off the stack when they're done processing. Each of these steps of the loop is basically a processing step. And yeah, what happens is it checks we're not on the last frame. As long as we're not on the last frame already, then what we're going to do is peek, take a look at the top thing on the stack, and peek means returning it, but we haven't removed it from the stack, and then we process it here. Then process frame basically takes one of 5 different steps, and these are the 5 different steps that could be repeated for each iteration of this loop. And so we might, for 2 or 3 steps in a row, actually be processing the same node frame, but sometimes we'll jump to the lower node frame, or sometimes we'll go back. So these steps all do quite different things. The first step we almost never use. The first step is if we find the node in the dictionary straight away, but actually there's another point that we check the dictionary that's almost always used instead. So don't worry about case 0, almost never happens. Case 1. Case 1 is actually, the thing is also like before with the expansion rules, it checks these in order, and these are kind of in a priority order. Case 1 is used when we get to the bottom of the tree, and it says, oh yeah, if it's case 1, what you want to do is return the value as 1. Whoops, looking over here. What happens in case 1? Yeah. And we know we're at case 1 when remaining blinks equals 0, then we're at the bottom of the tree. What happens is we add our value to the dictionary, because we worked out what it was, but only for the bottom of the tree, so that's a little pointless. Doesn't matter. Then we pop the stack, because we're removing things when we get to that step that gets to the bottom of the tree. So you can see 2024 is on the stack, but then it's popped off the stack. It's count. Oh yeah, only if there's items on the stack still. I think there almost always should be if we're at the bottom, but theoretically it could not be. Then we want to look at what's next on the stack. So peek. At this point, because we just popped, what's back on the stack is its parent when we peek the next item, and then we add to accumulated, add the count to that item. And that's how the counts go kind of transmitted back up the tree. Next case, so if it's not the case that's the bottom of the tree, then that's the expansion case, which we've seen already. And then it goes into nodeframe.expand, and nodeframe.expand basically has those same 3 rules that we've seen before in terms of add, split, or multiply. I probably don't need to go into those. I think you kind of might get how they work. Maybe what's important is when it does those, the results are added to this children list. And so it's always doing expansion before the next steps in here, the next rules. So any node will be expanded first and have its children added. The next steps we go to do processing of the children. So you're always doing expansion before that and adding either 1 or 2 children to your node. Okay. The next one is processing the children. And processing the children has 2 cases inside itself. The first, again, is it tries to get the value from the dictionary. And this is actually where it almost always catches that there's a dictionary. So here what it's doing, so in step 21, we resolved that this 20 on the left has 3 steps. Step 22, it actually didn't get as far as adding that to the stack. It said, I'm going to do my second process children step. I do have a 20, and that's when this first case runs in case 3. The second case in processing the children, I should make this bigger. It's a bit annoying, isn't it? Sorry. The second case in processing the children is when it didn't find it in the dictionary, and of course, so we actually need to do the processing, and that's when we're creating a node frame and adding it to the stack. So that's when we're doing, let me go back until we do it. Yeah, here we go. This is doing that. So it's saying, okay, I worked out that 1 is my child, and now is the step where I've actually added it to the stack, so it's the next thing that gets processed. Okay, case 4 is when we're all done, and that's when we're climbing back up the queue, back up the stack. So now we've popped that, we've worked out the count, and case 4 runs now because it says, actually, you've got no more children to process. So it runs, so case 3 would run if there were still children to process. If that's not true, then case 4 runs, which is, yeah, all the children are done. It's also, the expansion has to have been done for us to reach case 4. So that means the node's complete, and that's when it basically does a similar thing to what's done back here at case 2 when it's the bottom. It removes itself from the stack and accesses the parent after it's removed itself to add its count, its accumulated count, to the parent's accumulated count. And that's how the accumulations move up the tree. Is that clear as mud? Probably not. I think maybe if you try to do this problem yourself, or you've got a depth first traversal of a tree, then maybe a reference like that could come in handy. Personally, I needed quite a bit of reference material and checking some other solutions around the web to get it myself. But hopefully, yeah, this is something you could return to if you ever ran into this problem. Hope it's at least been interesting for you. Okay, that's day 11. Obviously, quite a few things going on in my life. Let's see how far I get through the other days, but hopefully I finish the advent of code 2024 before the advent of code 2025 starts. Either way, it's been great. Learned a lot. Thanks again for your support and time watching. Catch you soon.